Hello everyone. The topic of the presentation I'm planning to make today is technical, economic, and environmental analysis of a power electronics-based hybrid renewable energy system for remote communities in Newfoundland, Canada. As we understand it, that in so many remote communities in Newfoundland, and their power supply used to depend on the isolated power system, so they are facing a huge challenge like the high cost, unstable power supply, and environmental pollution. Besides that, they also have to completely rely on diesel for power generation. So the objective of our research is to design a wind power diesel energy storage hybrid system, and so that we can enhance power supply reliability, reduce cost, and cut carbon emissions. On this page, I will make a simple introduction about the system architecture and the component configuration. The whole hybrid system is designed based on the Homer Pro modeling optimization, and in addition to that, I also collected some data from on internet about the remote place Black Tico in Newfoundland, where the wind speed is over 7 meters per second during the whole year, and the annual electricity demand is over 1,000 megawatt per hour. So after making a simulation, we came up with the following architecture. So our hybrid system consists of two wind turbine, one diesel generator, one battery, and one converter. In the following part, I will make a simple introduction about the control strategy. The hybrid system will prioritize the wind resource first. So, like for example, when the wind is strong enough, and the wind turbine will start producing electricity. At the same time, the battery system will start getting the power as much as they can, so that when the wind is not strong enough and the battery could continue to provide power to the residents. But when the electricity in the battery system is lower, maybe it's less than 30%, we will start using the diesel engine, so that we need to make sure that the wind power penetration rate should be as high as possible. And besides that, we also have to make sure that the 100 power supply reliability. And in this part is about technical performance analysis, and we know that the power, about 85% of the power is from wind resource, and about 13% of the power is from diesel. And in addition to that, the excess power generation is too much, because as we understand that the wind resource used to be more unpredictable, so we cannot make sure that all of the power we produced will be equal to the requirement. We have to make sure that we have enough excess power generation, so that in the future we can not face the power shortage in the future. So at the same time, it also means that we need a huge storage system to save the power as much as they can. And for this part is about system stability analysis based on the Homer. In the Homer, I choose different I try to change the wind speed to make a further research about the key performance, and at the same time to analyze the stability of the system. So the first, when the wind speed was set at 684 meters per second, we know that the operating time of the diesel engine has increased by 43%. So we know that so when it comes to the impact of the stability, the fuel cost rises significantly, and the system stability decreases. But when we set the wind speed at 20 meter per second, we can know that the penetration rate of wind power has reached 87%, and the annual throughput of batteries soared by 56%. So we know that the energy storage system are facing severe test. And finally, we choose to set the wind speed to 12 meter per second. So we know that the levelized cost of energy remains at $0.91 per kilowatt hour. So it means that the optimal balance between economy and reliability. So in conclusion, we know that the proposed wind diesel storage hybrid system has good adaptability within a wide range of wind speeds, but there is a significant trade-off between its performance and economy. And in this part is about economic analysis, and we know that the whole money and the whole cost of the hybrid system is about $13.6 million. So when it comes to its cost structure, we know that over 70% of the money will be spent on a storage system because as we have mentioned above that the renewable sense is unpredictable, so we need more money to increase the technical part of the storage system. And besides that, the fuel cost of the diesel engines is also very high, and the long-term expenditure is significant. And the last one about the levelized cost of electricity is about $1 per kilowatt hour. I think this number is okay and it's not too expensive. And in this part, I try to make an adjustment of the carbon price, ranging from $0 to $100 per ton, to check how how will the architecture of the system and the levelized cost of energy change according to the different carbon price. So from the picture on the right side, on the left side, we know that no matter what carbon price we cite, the architecture of the system remains the same as previous one. So we know that the architecture of the system is stable enough to match with to deal with different price scenarios. And in addition to that, we know that as the carbon price increase, the levelized cost of energy increase slowly. So it means that it didn't have a dramatic effect on the cost of energy. So we got the following conclusion about the carbon pricing and policy scenarios analysis. The first one, the levelized cost of energy, rose slightly with carbon price, and the system structure is stable and its configuration has not been adjusted due to carbon prices. And besides that, the carbon price policy has a limited impact on the economic efficiency of the system, but it has an environmental incentive effect. So and in this part, we will talk about the door factor sensitivity analysis of diesel price and carbon price. So we know that when the diesel price are very low, the increase in carbon price has a more obvious impact on levelized cost of energy. And on the contrary, when the diesel price are high, the impact of carbon price weakens. So based on the two results we have got above, and I came up with the following policy recommendations. So the first one is the price guarantee mechanism. The objective of the policy is to hedge against the risk of fluctuations in diesel prices. And we can choose to do that by establishing a regional diesel price stabilization fund. And besides that, we could also sign a long-term fixed price fuel supply agreement. And the second one is carbon price guidance policy. So the objective of that part is to promote the decarbonization of the system gradually. Like it can start with a lower tax rate of 30 US dollar per ton, and it can also take advantage of its marginal incentive effect to avoid causing an impact on the community economy. So the third one is investment incentive policy. The objective is to reduce the upfront cost pressure on the key components of the system, and it could also provide a one-time investment subsidy of 20% for energy storage and wind power equipment. So in this part, I will conclude what I've learned from my project, and I can divide it into two parts. The first one is system design and performance, and the second one is economy and policy adaptability. So when it comes to system design and performance, I got that a wind power diesel energy storage hybrid system was successfully designed and optimized for remote community in Newfoundland, Canada, and it also achieved a high wind power penetration rate of over 80%, and it realized 100% power supply reliability. So when it comes to the economy and policy adaptability, the system has demonstrated good economic adaptability to carbon price policy. When the carbon price rose from $0 to $100 per ton, the cost per kilowatt hour only increased slightly. And besides that, the fluctuation of diesel price is a more crucial factor affecting the economic feasibility of the system. If we really want to reach net zero emissions in the future, there are still so many things left to be done in the future, like the system optimization and the comparison. We need to levelize multi-objective optimization software, a more precise, comprehensive analysis of technology, economy and environment is conducted to seek the optimal configuration of the system. And we also need to deepen the research on policy tools focused on analyzing the differential impacts of carbon pricing and the initial investment subsidies on different types of communities, such as fully off-grid and hybrid energy communities. The third one, we need to formulate specific policy guidelines. We need to provide data-driven decision support for the environment government, clearly defining under what conditions carbon taxes, subsidies, and combined policies should be prioritized to most efficiently promote the clean energy transition. And that's all my presentation. If you have any question, please feel free to let me know.